Okay, good morning everyone. So today we'll continue for the PN, this kind of device. But last time we mainly talked about the PN junction. So today we focus on the device. So since we have already understood the basic transport in the PN junction, so now we'll move on to the understanding of the device characteristic in the PN diode. So first of all, we will be interested to understand the current flowing inside the PN junction. So in the case of the PN diode, the operation of the PN diode, basically we have the three different cases. The first one is zero bias. And second one is we have the operations under the reverse bias. And also we have operation under the forward bias. The basic idea characteristic for the diode, of course, we will have the solely improvement later, but right now you can start to look at the basic IV characteristic for the PN diode, which is a typical, since the diode is only the two-terminal device, so we actually only apply the voltage in the anode side. So we only have the anode current versus the anode voltage here. And under the case of the forward bias, the characteristic for the diode is roughly at a certain voltage, we will start to have the current increase here. So usually we define this one as a forward turn-on voltage. In the meantime, if we apply under the reverse bias, there should be no current. So now we will try to understand why the electrical characteristic of the PN diode will look like in this way. So first of all, we're considering under the zero bias, and this is the point of the zero bias. So in the case of zero bias, we are now consider this is a PN junction. So we have the P type on the left side and then the N type on the right hand side. So in the case of the P type, we all know our Fermi level will close to our valence band. So we should have the band diagram like this. This is our Fermi energy, EF. And this is our conduction band, this is our valence band. And this is, since this is under the case without given any bias, so the Fermi energy should be the flat in the whole system. On the other hand, if you look at the band diagram in the N side, so that means our Fermi energy will close to our valence band, far away from our close to our conduction band, far away from our valence band. And therefore, in the N region, we should have the band diagram like this. And since this is in the one system, so the conduction band and then the valence band should be continuous. So therefore, we start to have this like this one. And this is how we already shown in the last lecture. And the difference between this gap that's usually we call as a potential barrier, and this is our building potential barrier, or we call it as a building voltage, as shown in here. So this is a case under the zero bias. And if now we consider under the reverse bias, so reverse bias, it means that we apply the VR, which will be minus VA. So that's our reverse bias here. So in this case, actually, we apply the negative voltage on the anode side, on the P side, and then positive voltage on the N side, which is the cathode side here. And under this case, let's start have the Fermi level difference in the P region and N region. So in the P region, we have Fermi energy here. In the N region, we have Fermi energy here. So that's our EFP. This is our EFN here. And of course, in the left-hand side, that's still in the P region. So that means our Fermi energy is close to our valence band. So we still have this similar like this one. So still the same. Under this case, the Fermi energies continue in the system. Therefore, we can expect the band diagram will become like this one. And this will lead to the increase of our building voltage, which will be VBI plus VR, which is our reverse bias voltage. And in this case, once we consider we have electrons in the N region, which is not be able to flow to the left because the barrier, potential barrier, is increased. Also, if we consider the holes in the P region, which will not be able to flow to the right hand side, this is because the barrier is increased. So that's why ideally we can expect once we increase the reverse bias, they should have no current because the barrier is increased, and then the barrier height is increased, and that will make this carrier will be more difficult to flow from right to left or from left to right here. And since the barrier is increased, so we can also expect the depletion width is increased as well. So that's a case under the reverse bias. And then the last case will be under the forward bias. In this case, we apply the forward voltage here, and our applied forward voltage will be equal to positive anode voltage here. So that means we start to apply the positive voltage in the anode side, which is a P type. And therefore, similarly, we still have the EFP in the left hand side. We have the EFN in the right hand side. But now we can see the gap here is different. So in the left hand side, we have the negative voltage, but right now we apply the positive voltage here. So in this case, if you try to plot the whole band diagram, still the same. This is a valence band, conduction band, conduction band, and valence band here. The main difference between the forward and reverse is that the barrier height is actually reduced. So now VBI will be the total, the new VBI will be equal to the VBI minus V forward bias here. A, this is a VA. And this is a positive, this is a negative here. So now the potential barrier is actually reduced. The potential barrier reduced, that means the electrons in the right hand side can start flow to the left, and the holes in the left hand side can start flow to the right, and the depletion region here is reduced. So that's why we start to foresee there will be the current flow under the forward bias. This is because our barrier in this region is reduced, and finally our carriers can be moved from right to the left, and also the left to the right. So that's the summary for the carrier flow, the physics for the carrier flow in the PN junctions here. So as I say, basically, if we can use the Venn diagram properly, then we are able to analyze most of the device physics. So like this is a case, for example, in the case of the PN diode, the Venn diagram already can help us to understand why the current voltage characteristic will be look like in this way. Okay, so let's go through the text together. So there will be the diffusion hole from the P region across the space charge region, where they will flow into the N region. And similarly, there will be the diffusion of electron from the N region across the space charge region, where they will flow into the P region. Then flow of the charge. In the end, the flow of the charge generates a current through the PN junction. So if we want to understand the current here, definitely we have to put the focus on all these charge flow. And next one, we have to derive some of the equation for the IV curve in the PN diode. So first of all, there's some like the assumptions. So the ideal current voltage relationship for PN junction is divided on the basis of 4 assumptions. The first one is we only consider the abrupt depletion layer. So the abrupt depletion layer approximation applies. So the space charge region have the abrupt boundaries, and the semiconductor is neutral outside the depletion region. So that's the first assumption. The second one is we will consider the Maxwell-Boltzmann approximation. So the Maxwell-Boltzmann approximation applies to the carrier statics. And also in the third assumption, now we only consider under the low injection. And consider under the complete ionization. So the concept of low injection and complete ionization we apply to try to simplify the case here. And the total current is a constant throughout the entire PN junction. So individual electron hole current on continuous function throughout the PN junction. And also the individual electron hole currents are constant throughout in the depletion region as well. And there are some terms we need to define clearly here. So the Na is an acceptor in the P region, Nd is a donor concentration in the N region, and we have this 0 means this is a thermal equilibrium. Majority carrier, this is a thermal equilibrium. This is thermal equilibrium. Majority carrier concentration in the N region. So that means if we consider a PN junction here, so our majority would be PP0 and also the NN0, and our minority will be the NP0. So the electrons concentration in the P region under the case of the thermal equilibrium. So that's a minority carrier in the P region. And we also have the minority carrier in the N region. So that's a definitions come from here. So this is not correct. So this is minority carrier. This is minority carrier. So we have a minority carrier concentration in the P region and minority hole concentration in the N region here. And also we have the total minority carrier concentration in the P, total minority carrier concentration in the N, and this is just a minority carrier in the different location. And this is excess minority carrier, excess minority carrier. So you can look up by yourself. So here we try to define the term that we will use later on. So now we will start from the state by state. First of all, we're starting from our building voltage, where we already derived this in the last week. So the building voltage is related to our thermal voltage, natural log, your concentration product over your Ni squared here. Now we can rewrite the equation like in this way. And now if we consider this term, since this is under the completely ionization case here, so this part will be equal to N0, and also this part can be considered as NP0 here. So therefore we have the NP0 is equal to Ni squared over Na here. This one equal to this one, and therefore NP0 will be equal to N0 exponential minus VBI over KT. So that would be the rewrite of this one. This one will be equal to this. We can move NN0 here, so that will be leading to this term here. So this term tells us that the minority carrier electron concentration on the P side, which is this one, of the junction to the majority carrier concentration on the N side. So this is a majority carrier concentration on the N side. So has this kind of the correlation. So again, this equation tells us that this is a minority carrier concentration on the P side is equal to the majority carrier on the N side times exponential minus VBI over KT here. So this is the meaning of come from this equation. Now we'll further derive. So consider the boundary condition here. We have this one, NP is equal to NN0 exponential. Right now we consider under the forward bias. So now we apply the forward bias positive VA here. So therefore this equation will be rewrite as VBI minus VA, and therefore we can further expand this one, becomes this times this one, and also this part is equal to this one. So therefore we have the NP is equal to NP0 exponential EVA over KT here. This is because these two terms. Okay, so similarly, we can have the equation of the PN is equal to PN0 exponential EVA over KT. So similarly, we have this one as well. So therefore, we can finally to also put some numbers in our Venn diagram under the forward bias. So this is the forward bias of the PN junction. So as we already shown before, we have the EFN, we have EFP here, and also we have this is our conduction band and valence band, and this is our conduction band and valence band. So we try to connect these together, and the difference between this one and this one is EVA. That's a voltage we apply. And since there's a voltage difference between here, so that's why our built-in voltage this gap is become EVBI minus EA. So that's why in the beginning we put this one here. So under the forward bias, so you reduce the potential barrier here, and therefore your voltage built-in voltage is changed from the VBI to VBI minus VA. So now we have some new equation, so we will be interested to further use this new equation. Actually, it's not really new, just some of the further calculation based on the old equation, but we try to have the concept here with minority carrier. We try to use the carrier in the P and N to place in this equation. So next is we will be also interested in like how actually the carrier concentration in the different PN or the depletion region here. So let's assume we have the PN junction like in this case. So we have a P type on the left hand side, we have the N type on the right hand side, and as we all know, in the middle we have the PN junction, and we also have a depletion region here. So this is our depletion region. So now if we're trying to plot the concentration for the different type of carrier with respect to the location. So this is our x-axis. X-axis is the location. So in the middle, we have x equal to 0, which is just right in the place of the PN junction interface. So we have x equal to xn. We have x equal to minus xp here. So if we consider the p-type concentration, the majority carrier of the p-type concentration under the thermal equilibrium can be plotted like in this way. So this is our NP0. So that's our majority carrier in the P region. Also, that's a minority carrier in the P region. So now we consider this is a minority carrier in the P region. And also, on the other hand, we consider the minority carrier in the N region, which is PN0. This is 0, that means this is under the thermal equilibrium case here. Right now, we all know, actually, we on the boundary condition here, we have in this place, we can also calculate the minority carrier concentration at this depletion region boundary, which is equal to minus xp. will be equal to NP0 exponential EVA over KT. So that's our boundary condition in the depletion boundary. Also, similarly, we can also have the minority carrier concentration in this boundary, which is PNXN is equal to PN0 exponential EVA over KT here. And actually, this part, the difference between this one and this is a thermal equilibrium. So the difference between this one and this one is our excess minority carrier. So I hope right now you can understand why in the previous class we actually spent the one chapter to explain if there is a minority, there's an excess carrier. Because right now, actually in the real device, we do have to consider there's an excess carrier. So in this case, the excess carrier is equal to NP minus NP0. But now you might be confused where this excess carrier come from. Since right now we are under the forward bias. The forward bias means that this is a positive voltage, this is a negative voltage. And from the previous Venn diagram, we already know under the forward bias, your potential barrier is decreased, and therefore your electron here can start to flow from right to the left. So now in this case, the electrons flow from right to the left. That is kind of like the additional injection of electrons in this P region. So this will become excess carrier here. So that's why we will have the excess carrier in the P region, because this is excess carrier is coming from the N region, because right now we are turning on this device, so we can expect the electron can flow from left to right. So similarly, the holes can also from left to the right, and once the holes flow from the left to right, the holes also will become the excess minority carrier in the N region as well. So that's why it will become these terms here. So this is also the excess minority, and will be equal to PN minus PN0 here. So the reason we have this additional minority carrier, this is because we have the electrons injected from N side, and these will become excess minority. In P side. So right, you have the electron here. Once they inject into this P region, so electron in this P region is actually the minority. But now this is additional electron, so that's why this is excess minorities here. So similarly, we also have this one, holes. So the holes injected from P side, and that becomes excess minority. In N side. So that's the reason we have this excess carrier in this boundary here. So this analysis is actually pretty useful because you will also face the same analysis again once we are dealing with bipolar junction transistor like a PNP or NPN, because we also have to discuss again the minority carrier injection from one region and reach to another side become the excess carrier. So now we try to apply some of the equations that we already know before. So first of all, this is an bipolar transport equation for excess minority carrier holes. So this is for the excess minority carrier holes in N region. So can be expressed by this term here. So this is the equation related to the space, related to the time. And also, the excess carrier can be expressed as shown here. So excess minority hole concentration is the difference between the total and thermal equilibrium minority concentration. So this is the one in here. So that's the excess minority hole concentration in the N region. So the bipolar transport equation describes the behavior of the excess carrier as a function of time and spatial coordinate. So we have the time here. We have x that's related to the spatial coordination. And to further calculate, we actually have to start to also consider some simplified case. So we assume the electric field is 0 in the neutral P and N region. Since the electric field is 0, so that means E is equal to 0 and there's no additional generation here. And also we assume this is the case under the steady state. So the steady state, that means the excess carrier with respect to the time is equal to 0. Is equal to 0 here. And therefore, this equation can be simplified as shown in here, where we consider the x is larger than xn, or the x is smaller than xp, and we define this one as these things. So therefore, our equation will become like in this one. The second order derivative of the PN, the excess PN, with respect to the location minus over LP is equal to 0. And similarly, we can have this one, the second order NP minus is equal to 0, and where the LP and LN is showing here. So that's our simplified equation once we consider the n bipolar transpose equation. And to further derive, we have to move to the experience we learning from the engineering mathematics. So as shown here, so we have this equation which is x larger than xn, so that's this part. We have this equation which is x smaller than xp, so that's in this region. And the general solutions can be shown in here, so we don't do this calculation. But with considered boundary, so we have the different boundary condition here. So this is boundary condition 1, which is this one. In the depletion boundary, and we also have this boundary condition 2. That's this. We also have once our x is approached to the infinite, and that means we can expect the concentration will be equal to our thermal equilibrium concentration. So that's boundary condition 3. And finally, we have a boundary condition 4 here. So we have these 4 boundary conditions, and we try to solve these general solutions. And luckily, the results are very simple. Of course, the experience might be tough, might be complicated, but in the end, the results are very simple. So the minority carrier concentration decays exponentially with the distance from the junction to the thermal equilibrium. Why we consider there's exponential decay? Because this term, that means we have exponential decay, and this will also suggest that we have the exponential decay. So now, if you come back to look at this carrier distribution, especially related to the minority carrier distribution, we have the x equal to 0, x equal to, this is xn, this is minus xp. And we also already know there's a thermal equilibrium minority carrier, that's a NP0. We also have know that there's already a thermal equilibrium, that's the PN0 here. And right now, this one is our minority carrier in the boundary, which is NPX, and this is on the minority carrier in the X here. So now, based on the equation, we can understand we have the exponential decay here. We have the exponential decay here, and that's our delta PNX. That's our delta npx. So we have the exponential decay function. We have the exponential decay function. So finally, we can understand these additional carriers is actually coming from the N region. So under the forward bias, so you have your electrons in the N region will start to flow across this depletion region and reach to the boundary. And once reach to the boundary, and this electron will become the excess minority carrier because that's located in the P region. But now this concentration for this excess carrier will start to decrease exponentially and finally reach to the thermal equilibrium concentration. Also similarly, the holes here will start to flow, reach to the end of our depletion region and become the excess minority carrier in the N region, and we start to exponential decay, reach to the thermal equilibrium concentration. So the process to have this equation is relatively complicated, but in the end, I think the result, if you try to just forget all this equation, understand the result from the physics point of view, I think that's pretty makes sense. Especially exponential decay function. This is very like the popular equation that's to describe the lots of the physics phenomena. So in the end, it's not surprise we have the exponential decay function, and also it's not surprise that the excess carrier in the end, anyhow, we're still back to the thermal equilibrium concentration. But now we have the very solid proof from the mathematical equation. Okay, so that's just the first starting point to allow us to understand the minority carrier concentration, the distribution of minority carrier concentration in the N and P region. But now we will be curious how we can further to calculate the PN junction current. So this is something I have been already drawn before. Since excess electrons exist in the neutral P region, here, and excess hole exists in the neutral N region. So we have these are the excess carriers in the N and P region, and therefore we can not only consider the simple Fermi level, we have to consider the quasi-Fermi level. If you back to the lecture when we talk about the excess carrier, in the end we also have the conclusion that under this the case with excess carrier, we have to use the quasi-Fermi energy here. So therefore, the total hole concentration is equal to P0 plus delta P, right? So the total carrier concentration in here, it must be the thermal equilibrium hole concentration plus the additional, and the N is equal to N0 plus delta N. And in this case, we have to use the quasi-Fermi energy to describe the concentration. So therefore, I have to draw the quasi-Fermi level. So in the left hand side we have this. This is our EFP. In the right hand side we have the EFN here. And of course, this is in the left hand side is a conduction bands here, valence bands here. This is conduction band, this is valence band. So we have EC, EV, EC, EV here. And right now, because we have to consider the, and then our intrinsic is here. Right now we have to consider the quasi-Fermi energy. So this become like in this way inside the depletion region, and then we have this. So, because in the previous we have already derived there's an exponential decay in the concentration, but in the band diagram, if we want to express the exponential decay, and that will be the linear. So this linear is because we have the exponential decay in the minority carrier concentration. So once we have this band diagram, so we can start to calculate the concentration. The total concentration in the P region will be equal to Ni exponential KT, and that will be EFI minus EFP, and that is our quasi-Fermi level. And similarly, this one is equal to Ni exponential, that's EFN minus EFI over KT. So this is EFP, this is EFN. So that's a quasi-Fermi and level. So that's a case that try to rebuild the band diagram come from the knowledge of the minority carrier concentration. So we have to consider the quasi-Fermi energy here, and also this linear is because of the concentration is exponentially decay. So the quasi-Fermi level are the linear function distance in the neutral P and N regions. And once at the space charge at the depletion boundary, we consider the low level injection here. Therefore, we can further reconsider the equation N0 PNXN is equal to N0 PN0 exponential VA over VT, and that's this one is exactly equal to Ni squared exponential VA over VT. So the N0 P is equal to this one. So that's a difference in quasi-Fermi level is related to the applied bias VA. This is something we already shown in the previous Venn diagram. And the difference between EF and EAP is nearly constant through the depression region. So that's why in here I draw the constant. And the total current right now is the sum of the individual electron and hole current. Which are constant through the depletion region here. So the total current should be the same no matter in which region here. But now if we look at only the depletion region, the total current is equal to the total hole current plus the total electron current in the depletion region. Since the electron hole current on continuous function through the PN junction, the total PN junction will be the minority carrier hole diffusion current plus the minority carrier electron diffusion current here. This one. So now, I hope you can understand why we have to put the focus on this point. Because the total current is always the same in the one system here. And therefore, we can use the current at this point and the current at this point to have the total current, which is shown here. The minority carrier hole current at the x equal to xn. So that would be this one. The minority carrier electron diffusion current, that would be equal to this one. So that's the point. It's a little bit tricky, but that's actually our goal. Try to have the current equation, because in the end we can use this plus this in the end to equal to the total current here. So if you consider the minority carrier diffusion current at this point can be rewrite as here, because now we only have to consider the excess carrier at this place here. And since we are considered uniform doped, so the thermal equilibrium concentration is a constant, now we only have to consider the excess carrier here. And the whole current density for this forward bias condition in the x direction can be written JPXN is equal to PN0 VA over KT minus 1 here. So similarly, the current can be from this one can be also expressed as Jn minus xp is equal to this one. And the total current density, as we have been already shown, just the one, these two plus together. So now the total current is become like in this one. And of course, the equation looks very complicated, but in the end, actually, we will definitely do some simplify in this case. So now we define this one as, because this is almost like the constant, as long as you have the concentration, but this one is related to the materials property, also material property. So it's actually independent of the bias here. So we can refer this term as a Js, and where Js is equal to and therefore we can understand our current is actually proportional to our EVA over KT minus 1. Especially is related to our bias here. So now, if it's forget all this equation calculation is fine, but now just the conclusion, just try to prove that our guess in the beginning of this lecture, I already made a guess that the forward current should be, this is typical the current in the diode, the anode current versus the anode voltage. So now from this equation, we are pretty confident that our guess is correct, because this plus already tells us that the current is a function of our applied bias. But now from the equation also telling the same things. And also we found out that the current is certainly exponential related to our bias. So that means our current should be exponential increase. So that's why in the beginning, that's why I draw, not draw like here, not draw like here. It's always draw in this way, because this tells us that there's a exponential, the current here is exponential VA minus 1. That's related to these things. So as I always say, this course is Semiconductor Physics and Device. So in the end, our goal is to understand the physics, using those physics, help us to analyze the device. But before we understand the physics, before we have to prove the physics is correct, we have to use lots of the complicated mathematical equations, try to prove our physics guess is correct. So in this process, during the process to prove the physics, sometimes it's complicated, but in the end, always the results are very simple. So finally, we have the total current is equal to this term, and where we define Js like this one. So the ideal diode equation can be expressed like here, and the parameter Js here is referred to as a reverse saturation current density. So now if we try to plot the reality but still ideally the IV curve, it should actually like in this way. So we have the current versus our applied bias here, and we have to apply a certain voltage. Once the voltage larger than certain voltage, we start to see the current exponential increase. So J is equal to Js exponential EVA over KT minus 1. And under the reverse, we actually have the small term minus Js here, which is reverse saturation current density. And of course, we all know it's not possible to always maintain such low current once we have the large bias. In a certain moment, it will start to increase and reach to the breakdown. So that's the real curve for our IV, the diode for the PN diode. And this is just some of the calculation. If you put a natural log and you try to decrease the VA, and then actually you can try to extrapolate the Js here. So the summary of physics here. So that's the whole picture for the PN junction current. Once we have forward bias applied to the PN junction, the forward bias will lower the potential barrier, so electron hole are be able to inject across the space charge region. So we have an electron here, we have a hole here, and the inject carrier become the minority carrier, which then diffuse from junction and recombine with majority carrier. So that's why we have this exponential decay here. So the minority carrier diffusion current decay exponentially in each region. However, the total current through the PN junction is still the constant here. So it decays exponential, but the total current is a constant. So we can use this one plus this one, and then we can get the total current here. So difference between total current and minority carrier is a majority carrier. So this one is a majority carrier, but actually we are using the minority carrier to analyze our current. So try to read the text by yourself and try to feel that whether you can understand. If you can understand the whole text with some of the explanation in the previous slide, that means you are actually fully understand what happens here. And of course, there's still some additional consideration we might need to be aware of. The first one is the generation recombination current, and then we have to also consider they have the chance for the high level injection. So by consider recombination, we have to apply the Shockley-Reed-Hall recombination series that where we have already described before. And under the reverse bias, it's possible to generate the current here. And this is because the generating electron hole pair with a reverse bias space charge region. So that means in reality, under reverse bias, there's not only the saturation, the Js term we have to consider, we also have to consider there's a reverse bias induced generation current. And the result here is also not that, from the physics point of view, actually it's not that difficult to understand. So once we have electron hole current generate, they are swept out from space charge region by electric field, and the flow of charge is in the direction of a reverse bias current. And finally, we also have to consider there's a generation current under the reverse bias. And what does this mean? This means that if we go back to check the IV curve here, we have a forward, and in the past we only consider there's a JS, but in reality the current is increased, and the gap here is somehow related to the generation current under the reverse bias. So under the forward bias, the electron holes are injected across the space charge region. So that's already something we have already known. So some excess carriers in the space charge region, some electron holes will recombine with space charge region, not become part of a minority carrier here. So that means actually once we have a holes here, holes will injected from the left to the right. We also have the electrons injected from right to the left here, and in somehow it is possible to have a recombination in the middle. And if you look at this, it's the recombination rate. You will figure out that in the middle there's a high recombination for these electron holes. So some of the electron holes will recombine inside this space charge region. So the total forward bias current density in the PN junction is sum of the recombination current, ideal current density. So therefore, the total current somehow has to also consider there's a factor contribute due to the recombination. So now if you look at the reality of the total forward bias current here, so in the beginning we only talk about this ideal diffusion current here, but right now the slope is equal to 1 here. But right now, if we also consider there is a recombinations happens, so that would be this one. This is related to the recombination here. So therefore, the total current is become here. So that's the total current. And this is a case that the recombination, so that means in the low voltage part you will see the some of the additional current. That's because due to the recombination. This is recombination under low injection. And the recombination will actually have the different slope here. So therefore, to evaluate, to consider all the case, sometimes we have the ideal current, sometimes we have the recombination current. Actually, in the end, we'll revise our equation with putting the N in here, where we call this as an ideally factor here. So for large forward bias, N is equal to 1. that means this is diffusion dominant. But for low forward bias, N is equal to 2. That means this is recombination dominant. So the N factor, the ideal factor, has become the very important the evaluation parameter to understand where our diode, where our carrier transport in the diode are ideal or not. Ideal, we want to keep this one as close to the 1 as possible as we want. But if you analyze your own device, especially if you analyze the diode, you found that your N factor is larger than 1. Sometimes it can be larger than 3 or 5. That means there are some mechanism dominate. That's why your current is pretty flat, cannot go very high like the ideal case. So finally, this will be the high level injection. So under the high level injection, at the case of the forward bias, once we increase a lot of the forward bias, we can expect that the excess carrier concentration increase and might become comparable or even larger than the majority carrier concentration. So this means that we consider the PN here. So we all know, now we apply the forward bias. We have the hole injection. We have the electron injection. But they could have the chance once if the injected carrier larger than the background doping. So that means you actually apply very large bias. Now your whole concentration inject into this region, and then the whole concentration is higher than the electron concentration here. Your electron inject into this region. Now your electron is higher than the whole concentration in this region. And this is high level injection. This is high level injection here. So now we have to also consider that they could possible to have the high level injection once our minority carriers dominate in the N or P region here. So starting from this equation, but right now because we have the additional carrier, so now we have to consider the N0 plus delta N and P0 plus delta P. And because right now our excess carrier is larger than the background doping. So our excess carrier is larger than the background doping. So this one is become this can be neglected, and now we only consider this equation now. And since the additional electron holes will be equal, so therefore this one can be considered as shown here, and where right now is related to exponential VA over 2 VT. So that means our current equation here is also related to exponential VA 2 VT. So that's also have this result. So that means if you try to have the current equation, log current versus you apply bias here. So we all know there's some part is ideal. And in the previous slide, we know in the low voltage is dominated by recombination. But right now, under the large bias region, also we have the high level injection. So that means your slope will be flat again, because right now the current is correlated with exponential VA to VT here. So that means after a certain moment, as long as you apply enough large bias, actually you won't get enough, your current cannot increase anymore because your slope actually will change here. So that will limit the performance. Under the high current operation. So if you want your diode, your PN diode, operate in the pretty high current operation, then you have to consider this high level injection, because this high level injection will limit the performance of the PN diode. Okay, so that's the last slide for this lecture. And the reason that I don't have the break, because I want to finish the class earlier. So we will end the class right now. And just reminder that we have the midterm exam tonight, in this evening at 6:30, and the same location, just in this classroom. So if any question, just let me know. Otherwise, we will see each other again in the later today. Okay, bye-bye.